Hello, class. This would actually be the fourth lecture that I'm doing today, but in fact, it's only really the third lecture because what I'm doing is I'm doing the third lecture over again because I can't be beaten. That's I did the third lecture on nodal analysis. So I did two lectures on y delta and delta y and an example of that that should hold you in good stead for working with power electrical engineering in the future. However, I started working on a nodal analysis problem too, and this was one that I had sort of put together last night at about 11:30 at night, and I thought, everything's working out here, with the matrices and everything like that, and so I got it all done, and then I did the lecture, and as I was finishing up on the lecture, I was like, wait a second, that can't be right, because there can't be a 54-volt drop. And I thought, well, I've done something wrong here, and what it was uh, back in the original equations when I was writing down the nodal analysis equations, and I'm sure that you out there in lecture land would have said, oh no, Professor Grenquist, that should be a negative. And yes, in one case, it should have been a negative rather than a positive. And then, I ended up solving the equations. There's a set of three simultaneous equations with three unknowns. And then I solved it, but I solved it for two of the relationships actually worked in the circuit. And I guess I'm getting a little ahead of myself because I'm not even writing the circuit down here yet. So I got myself a new marker. I think it's working out pretty well, but let me just draw the circuit for you. So this circuit, and like I say, this is a nodal analysis problem and introduction to nodal analysis that I'm going to be doing here. And so this is a current source, a independent current source that is hitched up to a circuit. I'm just going to, draw the circuit here. I probably drew that a little bit too close, but it's just a current source. And so I want to tell you that that is a 450 milliamp current source that is going in that direction. Right, I think everybody can see the direction that it's going in. And it's going into a resistor, and that resistor is a 100 ohm resistor. Then I've got the circuit that also is going over here. This is going through a 470 ohm resistor. And then it is going to another 100, and this is a node right here, another 120 ohm resistor going down this way, right? But it also has a current source out here too. And this current source is going down in this direction. And that current source is going to be a 300 milliamp current source. I guess that doesn't really work out well if you go across the line there, does it? Anyway, it's a 300 milliamp current source. And then I have one more resistor right here. And that resistor value is going to be 330 ohms. So you can see we've got two current sources that are feeding into that circuit. So how do you think the current is actually flowing? Well, we know that this current is going to be flowing up and in that direction, right? And so we know the current coming back to it is going to be flowing in that direction. We've got a pretty good idea that the current's going to be flowing down through that first resistor, that 100 ohm resistor. Right? That's a pretty good idea. And then we also believe that this is probably flowing out in that direction as well, because that's 450 milliamps. So we're assuming that that's flowing in that direction. We know another thing. We know that this is definitely flowing in this direction, and we know what its value is. We know its value is 300 milliamps. We don't, you know, this one right here, since, oh, I forgot to put our ground in. Excuse me. Let me ground this right here. Usually, you know, the base of a power supply, but then how would you know? Because which of the two current sources are we going to ground? So I'm going to say that this is 0 right here. And I'm going to actually give these individual nodes that I've got here numbers. So I'm going to say that this is V1, and this node is going to be V2. This node is going to be V3, and this node is going to be V4. Does everybody see that? 1, 2, 3, 4 clockwise going right around the circle. And everybody can see I got 300 milliamp current, independent current source, 120 ohm resistor, 470 ohm resistor, 100 ohm resistor, 330 ohm resistor, and then another current source over here going in the, you know, sort of the opposite direction to feed into that point right there at V3. Okay? Does everyone see how that circuit is drawn? Now that is an interesting circuit. As a matter of fact, it's rather complex. We're going to work through it, of course, but it's rather complex to look at how that circuit is set up. You know, the circuit, as I've drawn, is going to sort of collapse into a 2D state where we can use substitution algebra to do it. But what I'm going to do is I'm going to do it both ways. I'm going to use the linear algebra techniques to solve it, and I'm also going to use substitutional algebra to solve it, and, and then show you that I come to the exact same result in both of those two cases. All right. I think I'll actually take a second. I want to grab a drink of water. I'll be right back. Okay, I'm back, and I got some tea, nice hot tea. I want to set this clock again. All right, I don't think we'll be going that long anyway, because we already gone for a few minutes anyhow. But this is an interesting problem, and what I want to do is I want to look at the summation of the currents at all three. Now we pretty much know that we're going to have, oh, where's my current pen? Here it is. We're probably going to have a current through here too. I'm not sure which way the current's going to go through here. So we're going to have to find out what V4 and what V1 really is before we know which way the current is going to be flowing, because we've got 300 milliamps flowing in here. So I'm going to put a line here, and we're going to assume that the current is going to be flowing, down, but could be the opposite way. So we'll see. Anyway, it doesn't really matter what it is. We're going to find out which way it is in just a minute, because we don't really need that information for nodal analysis. Now we're going to look at 4 different nodes here: V2, V3, V4, V1. We do know something about the currents and stuff that are flowing in and what the voltages are at each one of these points. So let's look at V1 first. So if I look at V1, that vertex, and let's just draw it down here. I'm just going to draw V1, and we're just going to draw. I hope I get through this. we'll see how everything goes. Now we know that coming in to V1 is 300 milliamps, right, of current. And we know that the current that's going to be coming in from the thing up here, let's just say that it is flowing in this way. That's going to be V4 minus V1, if it is flowing in that direction, V4 minus V1 divided by 120 things. So V4 minus V1 divided by 120 ohms, right? And it's coming in that direction. Now, if we assume that this is flowing out here, which I think is a pretty good assumption, then we know that this is going to be the difference between V1 and V2. So V1 minus V2, right? All of that divided by 330 ohms, right? So those are our currents that are flowing into that location, right? So why don't we just do a summation of currents right here? So for V1, our summation of currents at that location is going to be 300 milliamps in minus V4 minus V1. Let's put that in parentheses so we know that it's in there. There's a minus sign out front, so it's going to do something to it, over 120 ohms. And also minus this other one here too, V1 minus V2, right, over 330 ohms. So, and we know that summing all of those at one node is going to give us 0 amps, right? So that's the first summation of currents at V1. That's V1 right there. Now, we know something about V2. We don't really have to do V2 because we know that V2 is going to be 0 volts. And we're going to use that in this thing right here because we know that we have grounded that. And so V2 right at that juncture, since it's grounded, is going to be 0 volts. We can use that in the other 3 independent equations that we have anyway, and we're only trying to solve for 3 unknowns, so we should be fine. Okay, now that's at V1. Now at V4, let's look at V4. At V4, when we sum all of the I's, the currents, and let me draw V4 down here. V4 is this one up here, and so you can see that we've got, current coming in, current going out, and then current going either up or down. Now, we've said that this is down, so we're going to assume here that it's going to be flowing out too, because there's no other place it can go to in here. If it's flowing down there, it has to be flowing in here. So here it has to be at V4, it's got to be flowing out from what we're assuming. We're also assuming that this current is flowing in to that location. And we know what the current is that's flowing out. That has to be 300 milliamps, doesn't it? Right? So what are these other 2 currents? Well, let's look at it. At V4, we know that the current flowing in is going to be V3 minus V4. So this current right here would be V3 minus V4 divided by 470 ohms. And this current down here is going to be the current that's flowing out. So that's going to be V4 minus V1 over 120 ohms. Okay. Let me just make sure that I've got all these things correct. Hey, wait a second. Why is that a plus? And oh, wait, did I switch that? Oh, no. No, that's right. V1 300 minus V1 minus V2 plus. This should be a plus. Oh, wait, no, yep, that should be a plus. Why am I saying that? Because V4 minus V1. Right, yeah, because that's the That's flowing in to that location. So in, out, in, in, out. Okay, good. Thank God I caught that. But of course, I have it on my thing. I've already done it ahead of time here, and I knew that that was correct. Let me just check these other ones out. Yep, everything looks fine there. So that's going in, that's going out, and that's going out. So there we go. So I've got here V3 minus V4 divided by 470 ohms minus 300 milliamps minus V4 minus V1, let's put that in parentheses, divided by 120 ohms. And we know that has to equal 0 amps, right? Okay, so that's two of them. That's V1 and that's V4. We know what V2 is. So the only one that we really need now is V3, which is this one up here. So V3, let's look at the summation of currents for V3 equal to 0. Now, when we look at V3, let's draw V3 down here. We see that we've got current that's coming in, and then we've got current that's going out because we drew in V4. It's coming in that way, so it has to be going out that way. In fact, what I've sort of drawn this wrong, haven't I? Current should be like that. Then current should be like that. These should just be straight lines. And then, of course, we've also got the other current that's going down, and we're assuming that that is in that direction. All right. So, and that's where all of our pluses and minuses and everything come from. So let's look at it. What have we got going in here? We've got 450 milliamps. We know it's exactly 450 milliamps that's coming in. We also know that this voltage that is going out here, or the current, excuse me, it's going out here, is going to be V3 minus V4 divided by 470 ohms, right? And in fact, that's what's going in there too. And this voltage that is coming out of this is going to be V3 minus V2 divided by 100 ohms, right? So I've got 450 ohms going in, and then minus V3 minus V2, and V2 of course is 0, over 100 ohms coming out. And then I also have coming out minus V3 minus V4 over 470 ohms. Does everybody see that? Okay, so let's write that one down. And we're just really writing down, this of course is for V3. So 450 milliamps minus, I'm going to actually write it out. V3 minus V2, even though that we know that V2 is 0, I'm still going to write that out. Divided by 100 ohms minus V3 minus V4 in parentheses divided by 470 ohms, right? Does everybody see how I've put all of these three equations together? As a matter of fact, what I want to do is I'm going to put, we're looking at these three equations. These three equations still can be simplified so that they actually, and I'm going to show you the simplification just a second. I'm not going to put you through the pain of going through the entire algebraic derivation and simplification of these equations, because I think everybody can see how they break down. And in two of the equations very quickly, and very simply, we can solve for two of the equations. But what I want to do is I want to put these equations now. In fact, let's just take this last one that I've got here, right? 450 milliamps. You know, I can rewrite that equation with the 450 milliamps on this side of the equation. I forgot the 0 amps there, sorry. The 450 milliamps stays on this side, but all of these things go to the other side, right? And what would that really give us? That would give us, I'm just going to rewrite the equation here quickly, V3 over 100 plus V3 over 470 minus V4 over 470. And all of that is going to equal 450 milliamps. Does everybody see that? See what I've got here? If I bring these over to the other side, because V2 is 0, so V3 minus 0 is just V3. There's the V3 over 100. There's the V3 over, and it's positive, right? Because it's negative here, so if it comes to the other side, it becomes positive. If it's negative here, it goes to the other side, it becomes positive, right? But this one is positive here, so it goes to the other side and becomes negative. So really what I can say is that 450 milliamps is actually equal to 0.012128 times V3 minus 0.002128 times V4. Right? I've just done that so that I could figure it out here, and now I've got some numbers here. And you know, I can solve this. I'm just going to keep it like that for right now, and show that this is 450 and everything else. That is the equation. I'm going to actually use blue, or actually I'll use green. That is the equation that is going to be one of the equations in our matrix, right? For when we solve it with the matrix method rather than the substitutional algebra method. So that's one of our equations. That's this equation right here, and it's rewritten so that we have it in that regard. I could solve that equation. I can solve that equation for V3, and if I did, I would get that V3 equals, in terms of V4, 37.1 plus 0.175 times V4, right? Very important equation that we're going to use later to solve for the voltages all around this rather complex circuit with two current drivers. All right. So that's one equation that we have. Now we want to look at these two other independent equations and figure out what they are. You know, we could do the same thing up here with the next equation. You know, V4. Don't I have V1 over 120, right? If I take this over to the other side, that makes that positive, and then these things stay negative. So I've got a positive V3, a negative V4, another negative V4, and a positive V1, right? So let's write this out just like we did over here. So we had V3 first, then V4. So let's start with V1. So I've got V1 over 120 plus V3 over 470 minus V4 over 120 minus V4 over 470. See how I've done that? positive V3 minus V4 minus V4 and positive V1. And all of those are going to equal 300 milliamps, right? And then I can rewrite that and say that this 300 milliamps really equals 0.01136 times V1 minus 0.00833 times V4. Right? And that whole equation then is my second equation that I would either put in my matrix if this was a more complicated equation, or use in direct substitution. Now, right here you can see that we have one equation with two variables in it, so I can obviously solve one. I can solve the equation for one of those variables. Since we solved this one for V4 up here, why don't we solve this for V1 in terms of V4? So V1 now equals, wait, don't tell me I've got it. Where did I put that? V1, wait, where? I have it here someplace. Oh, wait, no, it's over here. That's right, I'm sorry. Is that right? V1 equals 26.4 plus 0.733 times V4. And that is correct. I remember that those two were absolutely correct. And I have the correction for the last one actually here too. But those two, if you run through this and you solve this equation, that's really just algebra for V1. Of course, how would I do that? I would take this over to the other side. That would become positive. That's why it's positive there. And then I would divide it out by 0.01136. And so that would give me, and remember, 300 milliamps is really 0.3 amps, right? So everything here is correct because I've changed this back to 0.3 amps, 0.45 amps. Always work with primary units, like I've always said in the past. All right, so if we do that, we then get the third, wait a second, oh, the 450, yep, and we get the third equation, and that equation, this one up here, yes, yeah, that very first, wait, it's 470, yep. Yeah, I got it. Okay. So the very top one up here is the one that we want to do next. And what I get when I just break it up is V1 over 330. Where did I get that? Right, I've got V1 here. This is staying on this side. So these are being brought over to the other side. No negatives becomes positive. So I've got V1 over 330 positive, right? Plus V1 over 120. And I've got same thing here, negative V1 over 120, so it's going to become positive on the other side of the equation, minus V4 over 120 equals 300 milliamps, right? And then if I wanted to break that down, I would say that that is, did I get that right? Wait a second, 474, wait a second, what do we got there? You know, I think I did the wrong one. I copied the wrong one down. Wait a second. 0.11, 36, yep, 3, nope, that's right, I was right. No, wait that was the 300, and I had V1 over 120, 171, 120, 300. Yeah, this, I wrote down the wrong one here. In fact, what I did here and what I've gotten out the other side is, see the 450, just a second. I got that one, that's right. Then the second one I did was this here equals 300, but that's V1 and V4. No, this right here, I'm sorry about that. This is really coming out of V1 and V4, and that would be the very top one, and that's not this. That's what I was doing here. This is the one that's supposed to be down here. Oh my goodness. So here, I'm just going to take this. That is the one that goes up there. And I'm going to take this. And this is the one that goes down here. I know it's late, but I wanted to get this done. But this is, and this, let's just say that this one is the, this one is the top one. This is V1. So this is from V1. This one here is the one from V3. And then, like I say, these are just supposed to be crisscross so that when I look at this, I've got V1 over 120. You see in the V1 here, the 0.0136, that's V1 over 330 plus V1 over 120. Should we do that and just see if that is right? And it is 0.0136. Yes, I'm hopeful that it is, but I'm sure it's going to be. I got 0.01136, so thank goodness. Yes. So this this one here is really going this way. This is the one from V1, and this is the one that we get from V1. I'll just put that there. This is the one that we get from V4, right? And that's the one that we're going to look at right now. So V4, 1 over 120 for V1. So that's going to be 0.00833 times V1. And that would correspond to the V1 over 120. And then for V3, that's what we've got, V3 over 470. So we've got plus 0.002128 times V3. And then we've got minus, because you see the two minuses for V4, 0.01046 times V4. And of course, that equals 300 milliamps, right? So that's what I have. I know the later it gets, the more mistakes I tend to make, but this is a good lecture, and I wanted to make sure that you guys got all of these. Now, as you can see, because I've got V3 in terms of V4 and V1 in terms of V4, I could also do this last equation in terms of, V4. And in fact, that's what I'm going to do is I'm going to take this last equation and I'm going to fill it in with the individual V's, V1 and V3, using substitutional algebra, and we're going to figure out what this is. So let's do that. So I've got 0.300 amps, right? That's how we start out, equals 0.0083 times V1, right? Well, let's replace V1 with 37.1 plus 0.175. So I've got 0.00833 times 37.1 plus 0.175 V4. All right, so everybody see that? I'm going to put brackets around that because that's the first thing we've got. Now let's do the second thing. So plus 0.002128, right? And then V3. Well, V3, God, it's so, I know, wait, let me just fix it up. Yep, took the wrong one, of course I would have. So V1 is 26.4 plus 0.733, right, times V4. All right, and then let's go to the next one, 0.002128, and this one is going to be 37.1 plus 0.175 times V4. All right, and there's a plus there. All right, and then we've got minus, and then put another bracket in for 0.01046, and then times V4, and of course this V4 is just V4, right? That's a 4. So there you go. We now have this. This is one equation with one unknown. So let's solve for something. So we've got 0.3 amps, right? And then if you look at the whole thing, 0.00833 times 26.4. 0.00833. I mean, I know that you're doing it on your calculators too, and everything else, and I'm giving you the time to do that, but I'm going to do it on my calculator, and I get 0.22, right? So where's that going to be? That's going to be positive over here, so that's going to be negative over here, isn't it? You know, what else we get just looking at this is 0.002128 times 37.1, right? 0.002128 times 37.1. And that gives us 0.0789. 0.07, wait, why is that 0.078 to, and that's not what we, that's not what I got there. Is it? I guess it is. Anyway, let me just put that in there. So what was it? 0.0789. And that is going to be a positive, so it comes over to the other side. That's a negative 0.0789. All right, and I just want to, yep. And then what we have to do is figure out for the V4s now. I'm going to put that on the other side of the equation. And I've kept all of the numbers over here, but now I'm going to do all of the V4s on the other side. So I end up getting 0.00833 times 0.733, and that gives me 0.06106, right? V4. So that's the first V4, and then I've got 0.002128 times 0.175 times V4, and that gives me 0.0003724. And then I've got minus 0.01046 times V4, and of course that gives me minus 0.01046 V4. So now I want to add up those V4s, and I want to add up this side. So 0.3 minus 0.22 minus 0.0789 gives me 0.0011, right, amps. And then on the other side of the equation, I get 0.006106 plus 0.0003724 minus 0.01046, and that gives me minus 0.00398. All right, V4. So V4 is going to be, it looks like, a very small negative number. Let's just wait, why did that times V4, and that is that. Yes. So anyway, 0.0011 divided by 0.003982 gives me minus 0.276 volts. So that's what V4 is. We've got V4, right? So we know what V4 is, and now we should be able to apply these to find out what V3 and V1 are. So V3 is going to be 37.1 plus 0.175 times minus 0.276. And that gives me 37.05 volts. And then let's find out what V1 is, because V1 is just 26.4 volts plus 0.733 times minus 0.276. And that gives me 26.19 volts. Does everybody see how that works and how we did it? I did have a little screw up here for my notes and everything, but I think everybody sees how we put that all together. Now I'm going to continue looking at this problem for in a little while, because I want to do the same problem, but I want to use matrices now and use linear algebra instead of substitutional algebra to do this. Same similar problem, and in fact, we're going to delve a little deeper into figuring out what the various currents are in all of these different places too. So see you at the next lecture, and that's going to be tomorrow morning, because I'm not doing any more lectures tonight. I think it's about like 9:30. So, all right. But I wanted to get this nodal analysis lecture out to you and show you all the things that are happening. All right. I'll see you at the next lecture.